All right. Hello. Welcome to Thursday tutorials. We can answer questions about the review assignment or the lab. Um, just kind of a reminder, things coming up. Your lab is going to be due tomorrow. Um, Wait, I think it was due yesterday. Did I put it due yesterday? I'll probably still take it until a little bit later. Um, you are going to have a test at the very beginning of next week, so your test review is on the College Board website. Um, so I thought that you didn't have to submit it and I could still grade it, but it looks like you do have to submit assignments. So if you don't mind going through your old assignments on the College Board website and just clicking submit, I just reopened everything. That way I can actually look at it. It's not letting me do what I thought it would let me do. So any assignments you have on the College Board website, go through and submit those. I reopened everything so you can look at those. Yeah, test. It's either going to be Monday or Tuesday. I don't know yet. I need to talk with Lambert to see exactly when we're going to put that. But yeah, we'll do a little bit more review on that tomorrow during class in the morning. So, specific questions. I saw Alondra had a question about the lab. So, any questions? Uh, do we need to turn on your individual data? So for the lab, we have over the three sections I put. You do all need to put your individual group member reports up. So you're going to rate your group member. The data and calculations, that's going to be part of the group that you're turning in. Yeah, what are the sections I put again? Um, Yeah, so you have your self evaluation that everyone will do, the lab procedure that each individual person will do, but the group assignment is going to be your data, your calculations, your graphs, and everything like that. So you just need one for that group part. You're welcome. And then, yeah, I did put that due yesterday. I know some people still had questions on it. So if you're still working on that, just get it in by today and I won't count the lab late. So if you still have questions on the lab, that's fine. So, any questions about the lab or review or just any concepts in general that you're unclear about? So, the test is going to be pretty much all over springs and pendulums. If you release a pendulum from rest from 90 degrees, what angle would force of tension be equal to mg? It would be. That's a good question. Um, it really depends. You would have to have a string that can't bend at all, so it would have to fall down straight, which wouldn't really happen. I mean, I guess you could do. Yeah, that'd be kind of a mess because you would have to do your centripetal force would equal to the tension minus mg cosine theta. Didn't I ask this as a bonus question though? Yeah, so you'd have to do that. So you'd have mass times speed squared over radius is equal to tension minus mg cosine theta. So you'd have to get your speed using conservation of energy. And if we start here and then we go down, I'm using angle theta here in order to get that cosine. Um, Yeah, so we'd have to get this height from here to here, which would be theta minus 90, or 90 minus theta. What am I doing? 90 minus theta. And then, yeah, you'd have to use conservation of energy. So, like, the height here would be the opposite. So your height would be equal to, opposite is going to be sine. So it'd be equal to the length times sine 90 degrees minus theta, which should just be cosine, right? And then we could substitute this in where mgh is turning into kinetic energy. And you could go through and then substitute this in, speed squared here. So you'd have what? 2gl cosine theta equals final speed squared. Then you should be able to put this all in here. And then, yeah, your radius should just be equal to L. So m2gl cosine theta divided by L equals tension minus g cosine theta. Two mgl cosine theta equals tension minus g cosine theta. Wait, no, the L went away. And then, yeah, just solve for, you would want cosine theta to equal 1/3 in order to get rid of the 3. And then, so yeah, it should just be inverse cosine of 1/3. Assuming I didn't make a mistake somewhere. Like 70.53 degrees, something like that. Is that a question somewhere? Or you're just wondering? Wait, sine 90 minus theta, that is cosine, right? I'm not imagining things. Any other questions? Anything about the warm-up? How's the assignment on the College Board going? The review for the test. It's hard. Well, do you have a specific one? I could look at the multiple choice ones. It looks like a lot of people aren't doing the multiple choice. Or not multiple choice, free response. Yeah, I think there's only 2 free responses on here. If this will ever load. Pretty wordy. Sometimes wordy is better than not so wordy, though. Sometimes it's the really short ones because they don't give you enough information. friendly. One or two. Two is talking about energies. We're going to do that in our warm up tomorrow, so maybe not that. Do you want to look at question 1 on the free response? If no one has any questions, we might as well do that. All right. So in a physics lab, a group of students are provided with a sphere of unknown mass, a roll of string, a ring stand, and a measuring device that are commonly found in a physics lab. The students must graphically determine the acceleration due to gravity near the Earth's surface by putting the sphere into simple harmonic motion. State a basic principle, law, or equation that the students could use to graphically determine acceleration due to gravity near Earth's surface by putting the sphere into simple harmonic motion. Well, conveniently, we just did a lab about this. So, what type of simple harmonic motion could we use? We have string, a stand, normal measuring devices, a sphere with an unknown mass. I mean, what are we making? A spring setup or a pendulum setup? I mean, probably a pendulum, right? Spring, unknown mass. So we can use our pendulum equation. So period of a pendulum is 2 pi times the square root of length divided by acceleration due to gravity. Well, that's good. We're trying to find acceleration due to gravity, so they're probably talking about using our pendulum equation. I need to get rid of the square root to get acceleration due to gravity, so I should probably square everything else. So I get period squared is equal to 4 pi squared, length divided by acceleration due to gravity. I could multiply acceleration due to gravity over and divide period squared over. So acceleration due to gravity would be 4 pi squared times the length of the string divided by the period squared. Yeah, this will get uploaded later. So you don't have to follow everything perfectly. It is recording right now, and it should go up within the hour after we're finished. Yeah, it's pretty much exactly like part 2 of the lab, where he found acceleration due to gravity is 4 pi squared times the length of the pendulum divided by the period squared. Yeah, and it just says give the equation. It doesn't say explain it. So part B is where they say actually design the procedure. So this is our equation we could use for part A. So what would we need to actually follow through and make a procedure about this? Yeah, we want to graphically determine. Well, I don't need to measure 4 or pi. So what do I need to measure? Length. All right, so length. And then the symbol for the quantity is L. And it's in meters. And equipment to measure length, just meter stick. All right, I need to get period. What am I going to measure period with? With a timer, right? So that's really all we need to put in for this measurement. That's enough to get acceleration due to gravity. I don't need to record anything else. Um, Describe an overall procedure to be used referring to the table. Include any steps necessary to reduce experimental uncertainty. Provide enough detail so that another student could replicate the experiment. As needed, use the symbols listed in the table and include a circuit diagram. That's a weird way of. Include a diagram of the setup. I don't think they meant to say the word circuit. All right, so they pretty much set this up for us. I mean, attach string to the stand and tie the sphere to the bottom. Of the string. It's really all we need about the setup. We could draw our setup. We just have, here we have our stand. Here we have our string. Here we have our sphere of unknown mass. Someone's going to be over here with a timer. Yeah, this will be uploaded. It'll be uploaded on YouTube and then it will be posted to Google Classroom, yes. Within an hour afterwards. All right, what do we do next? I'm not going to do everything for you. So, someone say what to do next. Write some words. Well, what do we need to do with the sphere in order to put it into simple harmonic motion? All right, so pull it back to an angle less than 10 degrees. Pull sphere back to an angle less than 10 degrees. And let go. All right, now, how are we going to measure this in a way that will reduce experimental uncertainty? Let it go for 10 cycles. So use timer to measure time to complete 10 cycles. To complete 10 cycles. And then we'll see our period is going to be that total time total divided by 10. All right, so use the timer to measure 10 complete cycles. There we go. That reduces experimental uncertainty. We're not trying to just measure one time. This is going to average out the error of starting and stopping my measurement. And then what else do we need to measure? Well, we measured period. We also need to measure someone type out what they think the next sentence should be. Do we plug values in the formula yet? Not yet, because we still need to get the length, right? So how are we going to talk about measuring length? Measure length using what and from where to where? So I measure length using a meter stick. From where to where? So what point do I start measuring the length? Probably where it's tied to the stand. Where do I stop the length at? The top of the sphere, middle of the sphere, or the bottom of the sphere? It's the center of the sphere. So it's going to be turning. Anytime I have something turning, we always want to go to centers of mass, right? Back to the rotational motion type thing. So measure length uh, of string to the center of the sphere using a meter stick. All right, so we have this. These are all the values we need. We needed time, the period. We needed the length of the string to the center. Now, it doesn't, we're not using our equation to do this. We wanted to provide enough detail so that they could create a table, and ultimately we're trying to solve for this graphically. Where does it say it? Yeah, B, design an experimental procedure the students could use to graphically determine the acceleration due to gravity. So to do a graph, how many points do I need? I mean, yeah, we definitely need more than one. The more the better. We're not actually performing the experiment. So yeah, let's definitely say as many as we want. Like, let's go bigger rather than smaller. We're not going to have to do all 10 trials. So repeat procedure for 10 different lengths of string. All right, so now we're getting 10 different lengths, 10 different periods. And then we can talk about graphing. So when I graph, I want my slope to equal this. So slope is what divided by what? Y divided by x, x divided by y. Which one of those? All right, so change in y over change in x. Change in y over change in x. So what am I going to graph on my y-axis? All right, so 4 pi squared L. So graph 4 pi squared times the length of the string on the y-axis. And then we're going to graph period squared on the x-axis. And then we're going to take the slope of this graph to solve for acceleration due to gravity. Now, I probably went in more detail. I don't think they were expecting you to talk about what to graph yet here. This is saying, no, it does talk about graphically. Yeah, we do need to talk about what we're going to graph based on what they said. So yeah, I mean, pretty much any procedure. On here, they don't really care so much about the setup. Just talk about, yeah, and it does need to be the best fit slope of the, I should probably say best fit line. And that's another way, taking the slope of the best fit line, that's another way of reducing experimental uncertainty. So that's a really good point there. Um, so yeah, so we start with our setup should just be really simple to the point. We just have a stand, we tie a string to the stand, and we tie the sphere to the string. We pull the sphere back a small angle, less than 10 degrees, otherwise it won't be simple harmonic motion. We let go. What do we measure with what? Well, we measure time with the timer. We let it go 10 cycles to reduce uncertainty. Our period is going to be that time divided by 10. Well, we also need to get length of the string, so we're going to measure the length of the string to the center of the sphere using a meter stick. So measure what with what. We went to the center of the sphere. Anytime we have something turning or rotating, then we're going to be going to the centers. All right. And then we're trying to create a graph. So to create a graph, we need definitely more than 2 points. Like 3 is still kind of iffy, but the more points, the better. So we're not doing the procedure. So I'm just going to say repeat this 10 different times. What are we changing? Well, I'm repeating the procedure for 10 different lengths of string, right? That's what I can physically change. That's the independent variable. And then when I change the length of the string, that changes the period. So I repeat the procedure for 10 different lengths. I'm getting 10 different periods. I look at my equation I got. I'm just going to graph everything on the numerator on my y-axis, everything in the denominator on the x-axis, and then draw a best fit line and take a slope. And again, this is the same thing as if they said linearize this equation. So we create a graph. This is our linear graph. Questions on that one? I think pretty much everyone should be able to say, hopefully figure out this equation because it has acceleration due to gravity and realize I need to measure the period of the pendulum and the length of the pendulum, and then just measure period with a timer, length with a meter stick. All right, well, we kind of got ahead of ourselves, so we already figured out what we needed to graph on the horizontal and vertical axis. That's the next question. Indicate below which quantities could be graphed on the horizontal axis or the vertical axis to determine the acceleration due to gravity near Earth's surface by using a best fit line. You may use the remaining columns in the table above as needed to record any quantities, including units, that are not already on the table. So we already talked about this. If we already answered something in a previous part of the test, one thing, don't circle that and then put an arrow down. How they interpret if you circle something and put an arrow is they just say that disappears from this and it goes into the next part. So if you're going to reference something, you could say like in the previous part, I get this, or we can just kind of start over and just go from that. Well, C, I know acceleration due to gravity is equal to 4 pi squared times the length of the string divided by the period squared. And again, slope is equal to change in y over change in x. So I'm going to put on my vertical axis is my y-axis. I'm going to put 4 pi squared times the length. On my horizontal axis, I'm going to put period squared, my denominator. And then, yeah, it doesn't actually say to prove anything. It just says, what would you graph? And again, anytime they say to linearize something, that's really all we're doing. Just solve for the variable, put everything in the numerator on the y-axis, everything in the denominator on the x-axis. All right. So far, so good. So the second part of this, the students determine that the slope of the line is m, derive an equation that can be used to determine. Yeah, there are mock exams. I haven't decided how I'm going to do it. I'm probably just going to give you one of those mock exams and count it as a test grade. It would just be the free response section of one, though. So you're probably still going to get a free response mock test, and we will do a lot of AP test review pretty soon. Like after this next test, we're going to be doing a lot of review, and a lot of what we're going to be doing in class is you just solving AP questions from previous years, and then I'll give you the rubric, you'll grade yourself, and I'll go through it, and then you'll get a perfect answer. So yeah, we will go through previous AP test questions, a lot of them, especially now that we've covered all of the topics we need to have covered. So it's all review for 6 weeks now. All right, so they determine the slope of the line is m. Derive an equation that can be used to determine the acceleration due to gravity near Earth's surface by using the slope of the graph that is described in the quantity. Yeah, I don't express your answer in terms of slope m and any fundamental constants. It's honestly weird that they asked this question because I felt like in order to get to this point, you have to have already done what they said. But whatever, might as well start back over. Period is going to be 2 pi square root of length divided by acceleration due to gravity. Square everything. Period squared is equal to 4 times pi squared times length over acceleration due to gravity. Multiply g over, divide period squared over. So acceleration due to gravity is 4 pi squared times the length divided by period squared. Slope is equal to change in y over change in x, or the vertical over horizontal. So I get 4 times pi squared times length divided by period squared. We see these two are equal, and therefore we know that the slope is equal to acceleration due to gravity. So again, even if we've derived something at a previous point and they're asking us something that sounds similar, it doesn't hurt anything to write it here again. How much extra time did that really take? And then if you're wondering what they were wanting you to do, they make it obvious towards the end by giving you a pendulum. So, I mean, you can always jump ahead and see if they're giving you something later on in the question that will help you solve it. So they pretty much just straight up told you, hey, you should be looking at a pendulum. So in a second experiment, the students attach the sphere to a string such that it undergoes simple harmonic motion between the points x, y, and z in the figure. Shown in the figure, points x and z are the sphere's maximum displacement from the equilibrium position. Point y is at the sphere's equilibrium position, and the sphere swings along the arc. The student cuts the string at point z. Predict the motion of the sphere after the string is cut in terms of the sphere's displacement, initial speed, and acceleration. All right, where do we start this? So y'all told me what to write. Some form of projectile motion. Let's start off where it says to talk about displacement. What's our displacement right here? Everything we've done from the beginning of the stream, yeah, it's on the College Board website. Yes, it's part of the review on the College Board website. So where's our displacement? Are we center, maximum displacement, somewhere between the center and the equilibrium and maximum displacement? Where are we at? Well, this is that. Maybe you don't have the picture up. Is that what it is? So we're at. So okay. So string is cut at z. So point z. X and z are at. So y is at equilibrium. So where's point z at? All right. So point P is at the maximum displacement. So point Z is at the maximum displacement. So what do we know is happening at the maximum displacement? How fast are we going at our endpoints? So how fast are we going at that maximum displacement at the endpoint? Am I going really fast? Am I stopped? Am I going like slow, medium speed? All right, so at that maximum displacement, we know our speed is 0 meters per second. All right, so in terms of displacement, initial speed, and acceleration, so I'm at my maximum displacement, which means my initial speed is 0 meters per second. Which way is my acceleration? Acceleration equals when I cut it, 9.8. But let's be more specific about that 9.8. Negative. So 9.8 meters per second squared straight down. All right, so this thing's cut, it's at rest. The acceleration pulls it straight down. So which way does this go? So downward, any side-to-side motion. It's not moving, gets pulled straight down. So falling straight down, or is it falling like a projectile this way? Yeah, falls straight down. So starts at rest and it just drops. So that's all of this one. So again, normally you're given an experimental design. I assume they're probably going to try to give every one of you an experimental design this year, but with a shorter test, it might not happen. So we just kind of have to see. I'm just guessing until they give us more information on April 3rd. The second question on here, it's similar to a warm up we're going to do next class. So I'll let you try to do that later. And then if you still have questions on it, I guess you could ask me during class because, yeah, there won't be other times outside of that. Any questions on any of the multiple choice? Again, you're not getting any multiple choice questions on the AP test or this upcoming test, but there's a lot of questions that can easily be turned into a multiple choice. Is everyone on the College Board website? Yeah, so if you're on the College Board website, if you tried some of these, let's try to find one of those. Like 1 through, there's 22 of them, right? Yeah. Find one of those that you were struggling with. Try 21. I like 21. "21 makes you think in a little bit more interesting of a way. A student attaches a block to a vertical spring so that the block spring system will oscillate if the block spring system is released from rest at a vertical position that is not at the system's equilibrium position." So they're pretty much saying it's released somewhere other than equilibrium, which means it's going to oscillate back and forth. So if I release it at equilibrium, it won't go anywhere. If I release it away from equilibrium, it's going to bounce up and down in simple harmonic motion. So which measuring tools, when used together, can be used to determine the spring constant of the spring? All right, meter stick. Okay, looks like the lab. Now, this is oscillating back and forth. So are my forces balanced? So stopwatch to measure period. So let's look at both of those. So I see meter stick and I say stopwatch. So probably if you're thinking of a meter stick, so meter stick, you're probably thinking of trying to use spring force is spring constant times that magnitude of displacement from equilibrium. That's definitely one thing that we can use to get that spring constant. Or we could be using the period is 2 pi times the square root of the spring constant divided by mass. Now the spring force, whenever I just put something on the spring and it goes and it stops, then it's really nice. If it's just hanging there at rest, then I know the spring force is equal to the weight. But if it's going up and down, then that spring force is not always equal to the weight. We're going to have times when they're equal, when the mass is at equilibrium, but we'll have times when it's not equal, not at equilibrium. So that's going to be a little bit harder to use. Not impossible, but more difficult. So which one of these deals more with moving? Which one of these is going to be a constant equation when we're moving? Spring force equation or the period equation? All right, so period, that is talking about motion. So yeah, let's try using this one because we are in motion. This is going to be dealing with motion a little bit more easily. This is still valid at all points. It's just this displacement is always changing, which means the spring force is constantly changing, which means it's going to be a little trickier to use this. We're going to have a lot more sophisticated measurements there. All right, so what would I need to measure? I already saw we can measure the period with the stopwatch. What's the other thing we would need to measure then? Mass with a scalar. An electronic balance. Electronic balance or a scale. There we go. And then we don't need to measure 2 pi. That's a constant. So if we have these two values, then we can get our spring constant. And a calculator. You don't necessarily need a calculator, though. An electronic balance, anytime you see the word balance, balance is just pretty much a scale. So why they use the word balance? Remember your lab when I was finding the mass of things? So balance is just something that can pivot back and forth. You actually can't really see this very well. But yeah, it's just something that can pivot, and you put masses on each side to balance them. So an electronic balance doesn't work that way anymore, but a lot of people use the word balance and scale interchangeably. So yeah, so balance and scale, you can use those words similarly. Yeah, like a scale the ancient people use. So they didn't have anything electronic, so they just put something on one side and something on another side, and they were just balancing torques until they got level. Any other multiple choice questions on here, or still questions on this one? Let's see. There's a decent chance you have one at home, like maybe for cooking. 10. All right, student X attaches an object of mass M. Well, pull this up actually. Student X attaches an object of mass M to the end of a string of length L so that the pendulum is constructed. Student Y attaches a mass M to the string length 4L to construct a second pendulum. Which of the following claims correctly compares the period of student X's pendulum with the period of student Y's pendulum? Now, what's the first thing we should probably do if we're comparing the periods of the pendulums? It's like the first thing we should write. All right, set up the equation. I mean, they're talking about periods of a pendulum, so we're probably using the pendulum period equation. 2 pi square root of length divided by acceleration due to gravity. All right, so let's just put some values in here. I mean, I assume both students are on Earth, so I have student X, we can call this period X, is equal to 2 pi square root, and they just use length L over G. What's different about student Y? What is the only thing student Y changes? Length. So that's the only thing that student Y changes. They have a length of 4L now divided by G. Now, I really want to see how different this number is than the 2 pi square root of L over G. So I can just take the square root of 4 is 2, and let's just leave that 2 outside of everything. 2 times the 2 pi square root of length divided by acceleration due to gravity. Right, so I'm trying to get these two things to be the same and figure out this number out front because we're trying to find the period of student X is pendulum compared to the student Y's pendulum. So ultimately, I want period X equals something, right? So we're trying to get rid of Y. So let's divide a 2 over here. So 1/2 period Y is equal to 2 pi square root of length divided by acceleration due to gravity. But what is this 2 pi square root of L over G equal to? That's equal to the period X. So I could see 1/2 period Y is equal to period X. So period X is 1/2 of period Y. So what letter is that? Actually, I think you all have different letters. So the period of student X is pendulum is half the period of student Y's pendulum. For me, that's letter D. I don't know what answer choice that is for each of you. I think it's scrambled. Will there be online test correction? Yeah, it's really easy to mix up the twice because it would be twice if you were saying the period of pendulum Y is 2 times the period of pendulum X. That's the nice thing about writing out the equations here. Um, I'm a fan of letting the math do the talking because if I do the math correctly, it'll be obvious. Period X is 1/2 period Y. If I try to think about it, it would be real easy to mess up. Is period X twice period Y or 1/2 period Y? There's just something nice about uh, writing it out and knowing for sure as opposed to having to think and second guessing yourself. I haven't decided about test corrections. I'm probably just going to curve it because corrections would be a bit difficult to handle. Yeah, probably just going to be a curve. Grading has been a lot more difficult online. $22. Yeah, this is a good one. All right, so we have this graph right here. A block of mass capital M on a horizontal surface is attached to a horizontal spring of negligible mass. The other end of the spring is attached to a wall, and there is negligible friction between the block and the horizontal surface. When the block is pulled to a position beyond the spring's natural length and released from rest, the block experiences simple harmonic motion. A graph of the force exerted on the spring as a function of the block's position is shown. A student collects data such that the force of the spring exerts on the block for every 0.25 seconds is plotted on the graph that is shown. Which of the following two claims is correct about the block spring system during the time in which the data were collected? And select two answers. So, first of all, what shape is this making? Yeah, it's a wave shape. So it's going to be a sinusoidal shape. So it's not going to be like V's where you're going up and down, it's going to look specifically, it's going to look like a cosine wave. So if we were to connect the dots, I'm not going to draw it perfectly on my paper, but yeah, we would see something like this is what we're looking at. All right. So now let's just go through these one by one. So the block has maximum acceleration at all times 0.5 n, where n is 0 or a whole number. All right, so 0.5 n. So that would be saying here at 0 seconds. And then 0.5 times 1 is 0.5 seconds. 0.5 times 2 is 1 second. So it's pretty much saying every half second, 1.5 seconds, I'm experiencing maximum acceleration. True or false? Yeah, why is that true? Well, I know spring force is spring constant times magnitude of displacement. Well, we don't assume it's true. Yeah, so if I'm at the maximum displacement, each of these points are maximum displacement. That means I have the maximum force, and I know force equals mass times acceleration. So if I have a big spring force, I'm not changing my mass. That means I have a big acceleration. So all these points that are furthest away from my equilibrium, right? Equilibrium is that 0 line in the center. Maximum spring force at maximum displacement means maximum acceleration. So my choice for A looks good. So max acceleration at times 0.5 n. So that looks good. Are your answer choices the same as mine, or are some of yours different? Are your letters all the same, or are they different from mine? Okay, they are all the same. That would make things a lot easier. Okay, good. All right, so B, the block has maximum spring potential energy at all times, 0.5 n, where n is an integer of the whole number. All right, so 0.5 n. All of these are talking about these points here. So that's good. I don't have to redraw anything. So does it have the maximum spring potential energy there? I mean, what's my spring potential energy? What's the formula? One half times spring constant times the distance from equilibrium squared. All right, so at these points, what can I say about that distance? All right, so that's our maximum distance from equilibrium, which means we have our maximum spring potential energy. That looks good. Well, 40 newtons, we don't know the distance though. So we don't actually know the energy. Notice the graph is force versus time, not energy versus time. Which I guess we could have used that even more easily for acceleration is force. We didn't even have to look at all this over here, but still good to look at. All right, C, the block will have a maximum speed at those times, all the 0.5 n, 0, 0.51, 1.52. Correct or not correct? Yeah, what happens at the endpoints? What do we have to do? Yeah, it stops. at the endpoints. Stops at our maximum displacement. Right, we have to stop going down in order to start going up. We have to stop going up to start going down. We have to stop going down to start going up. And we have to stop going up to start going down, right? So, no, those endpoints were completely stopped. And then D is talking about momentum, maximum momentum at these points. Well, let's just write our momentum equation. Mass times velocity. What's our velocity at these points? Yeah, 0. Speed equals 0. So because our speed is 0, that means our momentum is 0. So, no, we have absolutely no momentum there. What points would C and D be true at? Where would we look for C and D to be true? Where we have the maximum speed and the maximum momentum. Yeah, momentum is constantly changing throughout the whole motion, yes. Unless you want to get really technical, at these exact moments of time, momentum isn't changing. But yeah, it pretty much is constantly changing, yeah. So where would C and D be true, where we have the maximum speed and maximum momentum? Not at the maximum displacement, but at what position? I don't care about the number values. Yeah, at equilibrium. So at our equilibrium position, that's where we're going to be going really fast. And if we're going really fast, that means we're going to have the most momentum. So at all of our equilibrium positions, we're going to have the greatest speed and the greatest momentum. Other questions? So why maximum acceleration at endpoints? So one thing we can look at is just looking at our graph. If we have a big force, we have a big acceleration, right? So our endpoints are where we have the biggest force. Where we have our biggest force is where we're going to have our biggest acceleration. The other thing we can look at our endpoints, we have our spring force equation, right? So this is similar to a rubber band. If I'm far away, if this is stretched a lot, it's going to be a big force. Small displacements, small force. So if I go really far away from equilibrium, I have a big force, big acceleration. Yeah, these graphs are really tricky. That's a thing that a lot of people mess up a lot on. It's really weird how we have the most acceleration when we're stopped, and then we have 0 acceleration when we're moving the fastest. It's weird. It really is. 18. For this one, it's select 2, so it's A and B. All right, 18. A student attaches a block to a vertical spring so that the block spring system will oscillate in simple harmonic motion if the system is released from rest at a vertical position that is not the system's equilibrium position. Which of the following explanations is correct about why the system oscillates in simple harmonic motion about the block spring system's equilibrium position? Yeah, so we just have a vertical spring that's oscillating back and forth, up and down. So, like what we saw, just going back and forth, up and down. So, what makes this simple harmonic motion? This is a word we use a lot for simple harmonic motion. It has to do with the position. We do talk about acceleration, but we talk about acceleration in pretty much everything. There's a word that we've used far more frequently for this, for simple harmonic motion. It's not the first time we've used the word, but yeah, equilibrium. Equilibrium is a word that we use a lot here. And again, we use this in forces also, but what's different about forces is forces want to get us to equilibrium. So yeah, we know it's not C and D. Okay, so the system oscillates in simple harmonic motion because the block's acceleration is directly proportional to and opposite in direction to the block's velocity. Let's hold on to that one for a second. D, the system oscillates in simple harmonic motion because the net force exerted on the block is directly proportional to and opposite in direction to the block's acceleration. These are worded. Yeah. Yeah. It's not going to be C or D. So yeah, what's the best way? Yeah, let's just kind of look at this. So let's say this is my equilibrium position. So let's say, yeah, let's put it up here. Let's say I'm up here and I'm moving up. So my velocity is up. And it's comparing this to my acceleration. Which way is this accelerating? Down. So we're above equilibrium, so it's going to accelerate down. And then let's say I'm up here and I'm moving down now. Which way do we accelerate? Still down. That's what makes this simple harmonic motion, is we're always accelerating towards equilibrium. All right, then let's go on to this other side. So if I'm here and I'm moving away from equilibrium, which way am I going to accelerate? Up. And then if I'm here and I'm moving up, which way will we accelerate? Also up. So it's not that these are always the directions. So let's just go through these one by one. So the system oscillates in simple harmonic motion because the block's velocity is directly proportional to and opposite in direction to the block's displacement from the system's equilibrium position. So is the velocity is the velocity and displacement always going to be in opposite directions from equilibrium? So let's look at that phrasing. So yeah, the velocity is the velocity always opposite in direction to the block's displacement. Well, the block's displacement is up here and it's moving up. Here the displacement is up and it's moving down. Here the displacement is down and we're moving down. Here the displacement is down and we're moving up. So A isn't quite right because it's saying that the velocity is in the opposite direction to displacement. So A is not right. Because we could have a negative displacement and a negative or positive velocity. So looking at B, system oscillates because the block's acceleration is directly proportional. Let's not care about that for now. Let's just look at the block's acceleration is opposite in direction to the block's displacement. So is the block's acceleration opposite in direction to the displacement? So if my displacement is up, which way is my acceleration? Down. Here my displacement is up. Which way am I accelerating? Down. Here my displacement is down. Which way do I accelerate? Up. Displacement down, I accelerate up. So our displacement and acceleration, are these in opposite directions? Yes. So that part is looking good. My displacement and acceleration are always in opposite directions. And that's another way of saying if I go one way, I'm always getting pulled back to the equilibrium. So that's sounding really good so far. And the block's acceleration is directly proportional to the displacement from equilibrium position. So this is saying the acceleration is directly proportional to the distance from equilibrium position. Now, mass isn't changing, so I can multiply that in there. The spring constant isn't changing, so I could multiply that in there, right? These two values are constant, so they're not affecting whether these are proportional. So spring force equals that. So is my acceleration directly proportional to displacement from equilibrium? Exactly, yes. So yeah, so the displacement is always proportional to acceleration. Or another way of saying this, a big displacement gives a big acceleration. Small displacement gives a small acceleration. Okay. So B is looking really good right here. C is saying the block's acceleration is opposite to velocity. So yeah, we already talked about that. Acceleration opposite to velocity. That's not always true. Acceleration and velocity are opposite here, but same direction here. Acceleration and velocity opposite directions here, same direction here. So yeah, not opposite directions. And then D, the net force is in the opposite direction of the block's acceleration. Can the net force be in the opposite direction to acceleration? Yeah, the net force and acceleration are in the same direction. Yeah, net force equals mass times acceleration. Mass is a scalar, so whatever direction net force is, acceleration is in the same direction. Did you intend to write KKK? I think you accidentally put one too many Ks in that. Maybe just two Ks would be good. I'm pretty sure that's not what you meant, so. Yeah. I mean it might it might stand for something else, but it also has historical connotations that are not so great. Yeah, I don't know if it's like people use it for something else, but yeah, I wouldn't go around. There, some people might interpret that wrongly, even though I'm pretty sure that's not what you're intending. Any other questions? 7. All right. So we have a graph here. Again, the first thing we should probably look at, we have a force versus position graph. They put y there, so it's probably force versus a vertical position. So a 4 kilogram cube is placed in a container of water. A student observes that the cube floats. The net force exerted on the cube F represents the sum of the force of gravity and the force exerted on the cube by the water. A force probe is used to measure F as a function of the cube's distance y from the bottom of the container. Uh, the graph shows F as a function of y, where the positive direction is upward. Which of the following statements is correct about the motion of the cube if it is released from rest at a vertical position of y equals 0.05 meters? I gotta love them throwing in a physics 2 question. Uh, it is talking about the pressure of water and buoyancy. Um, I'll never understand why they throw in questions like that. But you don't need to know all of that about buoyancy. Let's see, what's the best way to kind of draw this out? Force exerted. Measure F as a function of the cube's distance. Yeah, so we could get. So it's released at a position of 0.5 meters. Yeah, so. Yeah, this is a weird question. Um, how are we going to. Yeah, how are we going to get acceleration from this? I really don't like this question for a physics 1 class, but you never know what they're going to ask you. Um the it's not going to be 9.8 meters per second squared. The problem is this cube is in water. So cube like the ice cube floats in water, right? So let's say this is the ice cube, this is the water. I push the ice cube down and then I let go. What's going to happen? It's going to float, and then it floats and then stops immediately when it gets to the surface, right? We're going to assume the melting doesn't have as huge of an effect over a short amount of time. So yeah, we're not going to deal with it melting over time. So it floats up to the top, but it has momentum. So what is it going to do? Just stop immediately when it gets here? It's going to bounce, so it's going to kind of go up and down, right? So that's kind of a simple harmonic motion. If I let go, it's going to be able to go up above and then back down below. So is there going to be a constant acceleration? So in order for there to be a constant acceleration, what also has to be constant? We would need a constant net force. Is our net force constant? No, our force isn't constant. We're going from at 0.5 meters, we have about a close to a 9 Newton force, and at 0.09 meters, we have about a negative 9 Newton force. So yeah, it's not a constant force. So we have a non-constant net force. So that means it can't be A or B, right? A and B rely on this being a constant acceleration. But we don't have a constant force, so we don't have a constant acceleration. All right. Now, let's look at what C is talking about. C is saying the cube will travel upward with a changing acceleration. So that sounds good. We definitely have a changing acceleration if we have a changing force until it comes to rest at a position of 0.07 meters. So why are they saying it stops here? What's their reasoning for saying it stops right there? So it's saying it reaches the equilibrium position and stops. Is the ice going to reach equilibrium position and stop? No, it has momentum. It's going to go past that point, right? But now it's gone up, and now we have a negative acceleration. So now we've jumped up out of the water with a negative acceleration. What are we going to do? It's going to fall back. It's going to kind of bounce between these 2 points. So which one is that? D. And it's not super clear what's happening. I don't think the cube is being pushed all the way down into the water. I don't think it's like jumping all the way out of the water. I think it's just, if I had to guess, I think they're trying to say the cube is just like oscillating slightly around that top of the water. Yeah, weird question, weird way of going about simple harmonic motion. But yeah, it's going to oscillate between these 2 points, between 0.5 meters and 0.05 meters and 0.09 meters. Yeah, I can't stop them from doing this. It's. I mean, it is technically a simple harmonic motion. Um, Fiction or friction? Unreal. It would. This would actually work. This would actually be simple harmonic motion if it's only pushed a little bit. So if it's oscillating about a small motion right near the surface, which this is a pretty small amount. I mean, depending on how big the piece of ice is, about a 4 centimeter difference. I mean, 4 centimeters isn't. I mean, 4 centimeters kind of like that maybe. So if it's a big chunk of ice oscillating about that, that would be simple harmonic motion, and this would be a realistic way of handling it. It's just a weird question because y'all don't learn anything about buoyancy in this class. All right, I guess I have time for maybe one more question before I have to go to a meeting. Gotta go now. Well, I guess then this might be a good time to go. Yeah, it's a teacher meeting for coordinating with MST and dual credit. So again, just a few quick things. On the College Board website, I thought I could automatically submit yours for you, but it wasn't letting me do that like I thought it would. So yeah, I reopened everything. If you don't mind going to the College Board website and submitting everything, that's kind of obnoxious. Things coming up, make sure you're getting your work in. I'll still take your lab today if you're still struggling with that. I haven't graded it yet, but I'll try to do that at some point today or tomorrow. Your test is either going to be next Monday or Tuesday. I'll try to figure out before then. I'll definitely post an announcement on Google Classroom. It's going to be all multiple choice, springs and pendulums, pretty much everything we've been talking about for a while. Or not multiple choice, but free response, all springs and pendulums. Um, the test is probably going to be through Google Classroom. Um, it is going to be 1 day to take it. Like, you aren't going to have more than that. So the test is going to be randomized. I created some fun ways of randomizing it. So if you try to cheat, it might actually make it more work. So yeah. And it's also going to be based on a curve. So the people who normally score higher grades have no incentive to help you because then they'll get less of a curve. And if everyone does extremely well, like above a 75, I'm probably going to just curve down anyways. So it's not in your best interest if you normally do well in the test to help people cheat. I'll put it that way. Um, so yeah, those are the things coming up after this test. It's just going to be a review for 6 weeks. So it's kind of nice. You're not having to learn new material from home. We're just gonna just every single day kind of grind out, do more and more review, and then hopefully you'll be ready for the AP test. So other than that, hopefully everyone's having a good day, having a good week, and yeah, see you tomorrow.